Hello everybody, hope you're doing well. I wanted to do a little follow-up on the radioactive decay curve and the dice that we did, and throw in a few problems on radiometric dating and how we figure out how old rocks are using this method. Say hello to my little fishies. Just got back in the pond yesterday.
Okay, folks, so here is the graph of our dice data. This one coming to you from Caitlin W. Thanks. Let's look at what it tells us. It shows that over time, the number of dice dwindles away, but it dwindles away in this curved fashion, which we call an exponential decay curve, which we might smooth out like this. And it tells us how long it takes for half of the dice to disappear. So if we look on the graph, right here, this is when half the dice were gone. And the question is, how long did it take, or how many rolls did it take for that to happen? So all we do is come down from the graph, like that, and we see that it's somewhere between 4 and 5 rolls, which I think most of you figured out. So that is the half-life. That is one half-life. And we can check this by looking at what happens after another half-life. Well, what does that mean, another half-life? Well, it means that we cut what remains in half again. That's right there. So, if we come down from the curve somewhere about here, we see that we're in the 8 to 9 rolls. So, 4 to 5 is one half-life, 8 to 9 is the second half-life. Let's check one more time. Come across about here, and we'll come down about here, and we see that we're at somewhere around 13 rolls. Yep, that's about 4 or 5 more. When you go from 4 to 5 to 8 to 9 and somewhere around 13, that's another half-life. And it just keeps on going and going, cutting in half each time. Percent-wise, well, the last question on the last assignment was what happens when you cut it in half again. So here's 1, here's 2, and here's the third. This is 50%, this is 25%, and this is about 12.5%. And if you kept going, you would see that it would go down to 6.25, and then 3.125, and you just keep cutting in half. All right, let's do a couple of sample problems, and then I'll give you 4 or 5 questions in the assignment. Here's a basic half-life curve, similar to ours, a little more smooth maybe. Okay? What I'm going to do is I'm going to give you the half-life of a substance, and then I'm going to tell you how much of the original substance remains, or I'm going to tell you how much of the product there is, which we actually call the daughter isotope. So we generally talk about the parent and the daughter. So you may see those terms. Okay? So if we had a substance with a half-life, which I'm going to write like this, of 1 million years, and in the sample, say a rock, right? Could be a rock, could be a fossil, something like that. In a sample of rock, there is 50% parent and 50% daughter. Isotope, right? That's what they are. They're called isotopes. Whatever it is, could be uranium and lead, could be potassium and argon, could be carbon and nitrogen, actually. How old is the sample? Well, if it's 50% of each, that means that we're right here. And how many half-lives gone by? 1 half-life. And how long is 1 half-life? You guessed it, 1 million years. So the answer is a million years. Okay, let's say we have another substance with a half-life of 500,000 years. in that sample, there is 25% parent and 75% daughter. How old's the sample? Well, that means we're down here. To get to 25% parent, how many half-lives? 2 half-lives. Times 500,000 each equals, again, 1 million years. All right, good luck. Let me know if you have any questions.